There's one curve in particular that is extremely common to need to parameterize, and that's a circle. So let's see how we can parameterize a circle. So let's start by parametrizing a circle with radius 3 that's centered at the origin, starting at the right-hand point of the circle and moving counterclockwise. And we won't worry right now about how fast we're moving around a circle. So whatever speed it comes out to be, that's what we'll have. So we're centered at the origin, and the radius is 3. So like this. And we're starting at this far right-hand point and going counterclockwise, so that means this way. Okay. So the key idea here is to parameterize a circle, right? Let's think about a unit circle for a second. So for a unit circle, as you go counterclockwise around a unit circle, if you have some angle in here, say theta, the coordinates of this point are cosine theta, sine theta. That's essentially the definition of cosine and sine, at least if you use the unit circle style definition. So cosine and sine, they're functions that are essentially made for parametrizing circles. So all we need to do to parameterize this particular circle is we need to figure out how to modify our cosine and sine functions so that they trace out this particular circle, right? They sort of automatically on their own, they trace out a unit circle, but we need to figure out how to trace out this circle. Well, the only thing that's different about this circle is that its radius is 3 instead of 1. So we can just scale everything up by 3. In other words, multiply both of these coordinate functions by 3. So that would give us 3 cosine theta, comma 3 sine theta. Okay. Now we can check that this really does trace out this circle because the equation for this circle is x squared plus y squared equals 3 squared. Right? This is the equation of a circle centered at the origin. Oops, I missed my squared. This is the equation of a circle centered at the origin with radius 3. To check that this moving point, this parametric curve, is always on that circle, x squared plus y squared equals 3 squared, well, how do you check if a point is on a circle? You plug the point into the equation and see if it makes the equation true. So let's do that. We get 3 cosine theta squared plus 3 sine theta squared, and we need to check if this is equal to 3 squared. So this is, let's see, 3 squared cosine squared theta plus 3 squared sine squared theta on the left-hand side, but that's 3 squared times cosine squared theta plus sine squared theta. And remember, we're checking if this is equal to 3 squared. But cosine squared plus sine squared, that's 1. So this is 3 squared equals 3 squared. All right, so now we can ask ourselves, for what values of theta was this point on the circle? Well, this equation is always true when we plug in our parametric curve. So this moving point is always on the circle, just like we wanted it to be. So this parametrization that we wrote down parametrizes a circle with radius 3 centered at the origin, and it does move counterclockwise because as theta starts at 0 and increases, cosine starts at 1 and decreases, so the x-coordinate starts at 1 and decreases, and sine starts at 0 and increases, so the y-coordinate of the point that this curve describes starts at 0 and increases, and so that means that our point is moving this way around the circle. All right, so maybe the main lesson here is to parameterize a circle, use sine and cosine, and the radius of the circle will just show up in front of your sine and cosine functions. Of course, there are lots of variations on parameterizing a circle, so let's look at a few of them. Let's parameterize a circle with radius 2, but centered at 4, 3 this time, but starting at the right-hand point of the circle and moving counterclockwise. So if we forget about where the circle is centered just for a second, let's parameterize a circle with radius 2. So we know how to do that. Since we want to start at the right-hand point and move counterclockwise, we can just use cosine and sine. And then to make the radius 2, we'll just put a 2 in front of them like this. So that scales everything so that the circle has radius 2. All right, well now we need to modify this so that the center of the circle is at 4, 3. Well, right now, this parametric equation as we have it written now, it's centered at the origin, which is 0, 0. So we just need to shift this parametric curve to the right 4 and up 3. To do that, we can just add 4 to the x-coordinate and add 3 to the y-coordinate. And that will shift the center of the circle from 0, 0 over to 4, 3. And so we're done. Now this parametric curve goes around the point 4, 3 and radius 2. So it's going to go like this. If we wanted to, we could check that this parametric curve really does stay on this circle by writing down the equation for this circle and checking that this point satisfies the equation for the circle. The equation for this circle is x minus 4 squared plus y minus 3 squared equals 2 squared. And I won't plug this parametric point into this equation and do all the algebra. It works out basically like the last one did. But this point is always on the circle that we wanted. All right, so the sort of short version of this example is to shift the center of the circle, just add the coordinates for the center of the circle at the end of your coordinate functions. Okay, of course there's more we can change about a circle than just its center. So what if we have a circle with radius 4 and it's centered at the origin, but this time instead of starting at the right hand point, we start at the top of the circle, but still moving counterclockwise at whatever speed we turn out to be moving at. So there are a couple ways to handle this. So the only thing that's different about this example is we're starting at the top instead of at the right hand point. So let me draw this circle. So like this. And we're moving counterclockwise starting at the top like this. Okay, so think about the x-coordinate for this point. The x-coordinate for this point needs to start at 0, because this top point is 0, 4, because the radius is 4. So the top point, the x-coordinate has to start at 0, and it has to be decreasing. And we know we need to use sine and cosine. So to start at 0, we have to use sine, because cosine doesn't start at 0. So we have to use sine. But sine starts at 0 and increases, but we need to decrease. So we need to just flip it so that it goes negative instead of going positive. Of course, the radius is 4, so we have to put a 4 in there as well. All right, that's for the x-coordinate. Now for the y-coordinate needs to start at the top, and between sine and cosine, and minus sine and minus cosine, it's cosine that starts at the top. So cosine theta. And so the y-coordinate starts at the top and it initially decreases, but that's what cosine does. It starts at the top and initially decreases. So we'll use a positive cosine. Of course, to get the radius to be 4, we have to put a 4 there. All right. So this is one way that will work. This parametrizes this circle starting at the top and going counterclockwise. There's another way to do it, though, which is this. So this is a circle of radius 4, so we could just write 4 cosine theta and 4 sine theta. But this way of parametrizing the circle doesn't start at the top, it starts at this right-hand point. So what we need to do is add an initial angle, add the initial angle, pi over 2, to get us up to the top. And that means inside of our trig functions, instead of just theta, it should be theta pi over 2. So this is another way to write down a parametrization for this particular situation. In fact, if you use the addition formula for cosine and sine to expand these two trig functions, and then you do as much simplifying as you can, what you get is the first way that we parametrize the circle. So really these are the same, they just look different. All right, yet another variation on the theme here. What if we parametrize a circle with radius 5, centered at the origin, starting at the right, but moving clockwise instead of counterclockwise? Well, again, there are two ways that you might do this. Let's think about our circle. So we're going to start at the right-hand point and go clockwise, so that means this way. So now for our x-coordinate, the x-coordinate needs to start at its positive maximum extent, and it's cosine that does that, so we'll use a positive cosine for our x-coordinate. Of course, to make the radius 5, we have to stick a 5 in front of there. And the y-coordinate should start at 0, so we need to use sine, but it should start decreasing instead of increasing, so there should be a minus sign in front of our sine. And of course we need a 5 there too, so that it has radius 5. So this is one way to parameterize this situation. There's another way to think about how we're parametrizing this situation, which is this. So if we write down our normal parametrization for a circle of radius 5, that would be 5 cosine theta and 5 sine theta, right, like this. But this second parameterization that I've written down, that doesn't go clockwise, it goes counterclockwise, so it goes this way. Well, what we need to do is essentially reverse time, right? We need to run time backwards. And to do that, just put a minus sign in front of the parameter. So now we have a second way to parameterize to write down parametric equations for this particular situation. Of course, sine and cosine both have, some symmetry properties. Cosine is even, so having a minus sign inside of your cosine function doesn't really make a difference, so these are really the same. And sine is odd, so having a minus sign inside of your sine function is like having a minus sign outside of your sine function. So these two are the same as well. So these two ways of writing down a parameterization are actually exactly the same, just different ways of thinking about it. All right, for our last variation on the theme here, let's parameterize a circle with radius 4 centered at the origin, starting at the right, but moving clockwise at 8 units per second. So let's get the circle locked down first. So it's radius 4, we're starting at the right, and we're moving clockwise, so we're going to have 4 cosine minus theta and 4 sine minus theta. Right? These minuses are what make us go clockwise. But now let's think about, let's figure out how we can make this go 8 units per second. So the angular speed, when you have something moving in a circle, the angular speed is the multiple in front of your parameter here, right? I guess maybe it would be better if I used t instead of theta. So when you have something moving around a circle, the angular speed is the coefficient in here that multiplies your time, right? And the angular speed and the linear speed, which I'll write as v, they're related by the radius. So if you multiply the angular speed by the radius, you get the velocity that the edge of that circle is moving at. This makes sense in terms of units, because if we're measuring distances in, say, inches, then the units for radius will be distance units, so that's inches maybe. An angular speed comes in radians per time unit, so maybe that's seconds. And linear speed is in distance units per time unit, so that's inches per second in this situation. And so when you multiply inches by radians per second, you do get inches per second. Remember, a radian isn't really a unit. It's just sort of a note to ourselves that we're measuring an angle. So usually when you multiply a radian by some other unit, the radian unit disappears. That's actually perfectly normal. So this product, radius times angular speed, does give you the appropriate units. And in fact, radius times angular speed is linear speed. All right. So the radius for our circle is 4. The angular speed, right, the number that we need to put here, we don't know yet. So let's just write omega for angular speed. But we know the linear speed. It's supposed to be moving 8 units per second. So that would be 8 here. And then we can solve for the angular speed, omega. So divide both sides by 4. Omega is 2. So now we know we need to put a 2 in here. Okay. So if you know how fast you want the object moving around the circle to be moving, you can figure out what coefficient to put in here next to your time variable. Another way this shows up sometimes is you might know how long you want it to take to make a complete revolution. So let's actually do this one again, but now instead of 8 units per second, let's say it takes 10 seconds for 1 revolution. So since the radius is still 4 and we're starting at the right, we're still going to have 4 cosine theta and 4 sine theta. Since we're going clockwise, we need a minus, and let me not use theta, let me use t. Okay, since we're going clockwise, we need a minus. So again, we just need to figure out what is the angular speed, the omega that goes in here. And the thing to remember about sine and cosine is the period, so t is often the, capital T is often the symbol that people use for period. It's sort of unfortunate to have a capital T and a lowercase t running around, but that's what we'll do. In a sine and cosine, the thing to remember about the period is, so the period for sine and cosine is 2 pi, but if you have an angular speed, the angular speed times the period has to be equal to 2 pi. So you can rearrange this, so you either get the angular speed is 2 pi over the period, or the period is 2 pi over the angular speed. Well, in this situation, we know the period that we want, but we don't know omega, so let's use this equation. So omega is 2 pi over, the period is 10, and so that means omega should be pi over 5. So we'll put pi over 5 in here. Okay, so whether you know how fast you want your object to move, or you know the period that you want, both of these scenarios let you figure out the correct angular speed for your circle.